Dear students, in last class I had explained applications of the Gauss theorem, in which we have used few equations. Just very quickly we will recall, and then we will see more applications of the Gauss theorem. The first equation that we have used is for electric flux through a small surface, which is delta phi. So, what is delta phi? Delta phi is equal to E delta S cos theta, where E is the electric field, delta S is the area which is area vector, and theta is the angle between the two vectors, that is the E and delta S. To find the total flux, we use the same equation, but with a summation. Total flux is equal to algebraic sum of the flux through each small surfaces, which is E delta S cos theta. And most important, whenever we measure the flux, we have to make sure that electric field E is same at each and every point on the surface through which we are going to measure the flux. The next important is total electric flux through a closed surface in free space is equal to 1 by epsilon naught times the total charge enclosed by the closed surface, which is nothing but the Gauss theorem. So, using this, we have derived an expression for electric field at a point due to a charged spherical shell. So, we have two more applications of the same, and this question has appeared twice in the examination. So, we have to derive an expression for electric field at a point due to an infinitely long, uniformly charged thin straight wire. So, the first application was all about charged spherical shell, and now we have thin charged wire, uniformly charged thin straight wire, but it is infinitely long. Infinitely long means the length of the conductor. So, we are going to consider the conductor something like this. So, this length, okay, this L is much larger than the distance from the point, only then we call it as infinitely long thin straight wire. So, we will consider positive charges. Let this be positively charged. So, you can either consider negative charges or positive charges. So, only difference is the direction of the field changes. So, I have taken a uniformly charged infinitely long thin straight wire. I want to find electric field at a certain point here, at a point P, and at a distance r, at a perpendicular distance r. To find the electric field at that particular point, we are going to use the Gauss theorem. And to apply the Gauss theorem, I need to consider a Gaussian surface, which is an imaginary surface enclosing the charge. And in the previous derivation, we had taken sphere as the Gaussian surface for the symmetric nature. And similarly here, for the symmetry, the kind of the surface that we are going to assume around the point P is nothing but the cylindrical surface. So, here this cylindrical Gaussian surface having length L, and r is the radius of the cylindrical Gaussian surface. Now, we have to find the flux through three phases, one end face, the second end face, and the third one is the lateral surface. At this particular point P, what is the direction of the electric field? The direction of the electric field is perpendicular to the conductor. This is the direction of the electric field, E. You consider a small area here having value delta S. So, what is the direction of the area vector? The direction of the area vector is also along the same, because the area vector is always perpendicular to the surface, Therefore, this is the direction of the area vector. So, now area vector and electric field are along the same direction. So, what is the angle between these two? It is 0 degree. You consider this surface. to this surface, the area vector is here, perpendicular to the area. But the field at this particular point is along this direction. So the angle between area vector, which is here, and the electric field, which is here. So the angle here is 90 degree. At this point, the area vector is like this. Normal means perpendicular to the surface and outward. So this is delta S. And if I consider a point here, so the field will be in this direction. That's the E vector. So the angle between these two, it's a 90 degree. So now let's find the total flux through all the three faces. Okay. First one, second one, and the lateral surface. And let Q be the charge enclosed by this Gaussian surface. Q is not the charge on the entire conductor. Q is the charge enclosed by the Gaussian surface only. And we can always define linear density of the charge, which is lambda, is equal to charge per unit length, Q by L. So that the charge enclosed is equal to lambda into L. So now let us find the flux. The flux through this surface and the flux through this surface is a 0. Why? Because equation for the flux delta phi is equal to E delta S cos theta. Delta phi is equal to E delta S cos theta. Where what is the value of theta? Theta is 90 degree. Theta is 90 degree, correct? Yeah, theta is 90. So cos 90 is 0. So therefore, flux is 0. So flux through this surface and the flux through this surface is 0. If the flux through both the surfaces is 0, then we are left with only this surface, right? So what is the expression for the flux through, or what is the flux through the lateral surface? So let's measure that. So the flux through this small surface I am going to measure first, which is delta phi is equal to E delta S cos theta. What is delta phi then? E delta S, theta is 0, right? See here, theta is 0. So theta is 0. So it's E into delta S. That's equal to, because cos 0 is 1 here, correct? Now this is the flux. Now I want to find the total flux. The total flux is given by summation of E delta S. Total flux is given by summation sigma E delta S. This is the flux through only this surface, right? I want the flux through the entire lateral surface of the cylinder, which is phi is equal to E delta S. That is E into summation delta S. What do you mean by summation of delta S? Delta S is the small area. Summation delta S means the total lateral area of the lateral surface of the cylinder. Okay, that is E into what is the area of this lateral surface, which is circumference, which is a 2 pi r into L. Now that is the total flux. So that's equation 1. Now I can find the flux using the Gauss theorem, which is phi is equal to 1 by epsilon naught into the total charge enclosed by the closed surface. But we have already measured total charge in enclosed here, which is Q is equal to lambda L. So if I can write phi is equal to 1 by epsilon naught into Q is nothing but lambda into L. So we have again measured the total flux. So this is the total flux based on this equation. In terms of the electric field, this is the total flux in terms of the charge or in terms of the linear density. So now we can equate equation 1 and equation 2. So from 1 and 2, we get E into 2 pi r, E into 2 pi r, E into 2 pi r, L is equal to 1 by epsilon naught into lambda into L, lambda L, correct? So, this L will cancel. So, rearrange for E is equal to 1 by 2 pi epsilon naught into lambda by this R. So, this expression E is equal to 1 by 2 pi epsilon naught into lambda by R. You can even multiply this by 2 here, so that we can write the same expression in terms of 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught 2 lambda by R. So, hope you have understood this derivation, important one. It has appeared twice in the examination, which is a derive an expression for electric field due to uniformly charged, infinitely long, thin straight wire, where the expression is E is equal to 1 by 4 pi epsilon naught 2 lambda by R, where what is lambda? Lambda is the linear density of charge, where lambda is linear density of charge. Then what is R? R is the perpendicular distance, R is the distance of the point from the linear conductor. So, I will continue one more derivation in my next class. Thank you.